And this state space analysis, we have few definitions and representation of the state and state model, state transition matrix, and also state transition equations. So this is your syllabus for state space analysis. The first definition is state. What is a state? The state of a dynamic system is the smallest set of variables called state variables, such that the knowledge of these variables at t equal to t naught together with the knowledge of the inputs for t greater than or equal to t naught completely determine the behavior of the system for any time t greater than or equal to t naught. So this is the state definition. So what is state definition? So we find the state of the system at any point of time. So this state can be determined by the state variables. So we have one more definition, the state space analysis, that is state variables. So how do you find the state of the dynamic system? Using state variables, right? So how do you find the state for t greater than t equal to t naught together with the t greater than or equal to t naught? T equal to t naught and t greater than or equal to t naught, right? The state variables of dynamic system are the smallest set of variables that determine the state of the dynamic system, as I mentioned. So it will find the state of the system. System is dynamic system, right? So as a group here, we have some smallest set of variables. So we have one more definition in the state space analysis, that is state vector. These are all definitions. State vector. If n state variables are needed to completely describe the system behavior of a, then n state variables can be considered as n components of the vector x of t. Such a vector is called state vector. So if n state variables are needed to completely describe the behavior of a given system, then n state variables can be considered as n components of the vector of x of t. Such a vector is called state vector. So we'll find some. So if you have n variables, so these n variables are components of vector. So that vector is called state vector. State vector x of t, you can say. The state space, one more definition is state space. The n-dimensional space whose coordinate axis consists of x1, x2, xn axis where x1, x2, xn are state variables is called the state space. So it is a n-dimensional space. Okay. Now we have one more definition: state space equations. State space equations. So in the state space analysis, we have n variables, state variables that are involved in the modeling of the dynamic system. So in the state space equations, we have three types of variables. The first one is input variables. Second one is state variables. And third one is output variables. So far we have only two variables, these input variables and output variables. So we have one more variable called state variable to find the state of the dynamic system. Okay. So generally to find the state we use some memory elements, right? So generally integrators will serve this purpose. So integrators will be used as memory devices to find the status of the dynamic system. Right. Now if you model your system with all these variables, it is called state space equations. So that's about basic definitions. Let us look at the simple block diagram of the state variables or dynamic system with state variables. So let us have that control system block. This is a control system. Input variables here. The input variables are represented using U, U1, U2 till UM. You must remember this notation. And the output variables can be represented by Y1, Y2 till YP. You remember these variables. These are the state variables. So they are represented by X, X1, X2, Xn. So you must remember this M, P, and N. So this is the block diagram of your dynamic system with state variables, or I can simply draw using block diagram like this. That is matrix U and Y. So to find out the state, I can put here x. Can also put like this. Now, how do you represent these state variables? So generally, all the state variables are represented by first order differential equations. So generally, these are represented by first order differential equations. Okay. So if you have n variables, you can say n first order differential equations. So let us write them. So the first equation, it would be dx1 by dt. So which can also be represented as x1 dot, recall this, which is equal to function of x1, x2 till xn, comma, u1, u2 till um, right? Similarly, for dx2 by dt is equal to, so these are all state variables, right? It is also a function of x1, x2, xn, comma, u1, u2 till um. So that's how you have n differential equations. It is d x to the power of xn by dt is equal to x dot n, which is equal to f n. You can put three more dots here, x1, x2 till xn, u1, u2 till um, right? So this is the representation of state variables. It is represented by n first order differential equations. Right? So if you integrate them, then we get x I of t is equal to x I of t naught plus integral t naught to t. So fi of x1, x2, xn, u1, u2 till um dt, where I is equal to 1, comma 2, comma till n first order equations. Right. Or I can say directly x dot of t is equal to function of x of t, if we represent with some vectors, it is a time invariant. If it is a time varying function x dot of t, remember these are all functions. So it is a function of state variables, input variables, and time. It is called time varying. Right. Now our interest is to find the state model of linear time invariant system. Since we did all the analysis for linear time invariant systems. So let us look at the state model of linear time invariant system. So before that, this state space analysis can be applied to any type of system. So that is for electrical system, mechanical system, biological system, or any kind of system, you can apply this state space analysis. Time varying, time invariant, linear, non-linear, whatever it is. But our interest is to find out the state model of linear time invariant system. So let us find out the state model for linear time invariant systems. These are all basics only. The first one, state model of linear time invariant systems. So what are the linear time invariant equations? Again, the state equations are linear and first order differential equations. So each derivative of the state variable is a linear combination of the system states and inputs. Since it's a linear time invariant system, your state variable first order differential equations can be represented as a linear summation of the input variables and state variables. So let us write those equations. So in the place of function, you have a linear combinations of all elements. So your state variable x dot nth first order differential state variable x dot 1 is equal to since it's a linear time invariant system, we'll get a11 x1 plus a12 x2 plus a13 x3 plus till a1m xn plus b11 u1 plus b12 u2 plus b1m um. Okay. Similarly, x dot 2 is equal to a21 x1 plus a22 x2 plus a23 x3 plus a2m xn plus b21 u1 plus b22 u2 plus till b2m um. So this is how you can write all linear equations. So till xn, I am putting 3 dots here, x dot n, which is equal to a I am putting here also 3 dots, a m1 x1 plus a m2 x2 plus a m3 x3 plus 3 dots a mm xn plus b m1 u1 plus b m2 u2 plus all the equations b mm un. Okay. You can put 3 dots. Here are also 3 dots. No. So put this in the matrix form. You will get 4 matrices. That is I think we did some mistake in this. Yeah, we have a small mistake we did. It is TCN AN XN AN XN. This is also N1 AN1 AN2 N3 ANN. Right? Yeah. Now it's correct. So putting in the matrix form, now you have the equation x dot of t is equal to a into x of t plus b into u of t. Very important equation. the first state equation. So it can be written as in the matrix form. First matrix is x dot of t is equal to, it is x dot 1 of t, x2 dot of t till x dot n of t, which is n by 1 matrix, and matrix A would be A11, A12 till A1n and A21, A22, A2n. I'll put 3 dots here. AN1, AN2, ANN. This is n by n matrix. Similarly, U of t. So U of t is equal to U1 of t, U2 of t till M of t. Since you have m inputs, so this is m by 1 matrix. Where B is equal to B11, B12 till B one M, B21, B22 till B2M. I'll put here 3 dots till B N1, N2, B Nm. So which is n by m matrix. So this is your first state equation. Now we shall write the output equations. Have you all noted all these equations? Okay, let us write the output equations. So the output is y1 of t is equal to C11 into x1 of t plus C12 into x2 of t plus C1n into xn of t plus D11 into U1 of t plus D12 into U2 of t plus 3 dots D1m into um of t. Okay, so this is your first output equation. So next would be y2 of t is equal to C21 x1 of t plus C22 x2 of t plus 3 dots C2n xn of t plus D21 u1 of t plus D22 u2 of t plus D2m of t. So similarly, I have P equations. Since you have P outputs, yp of t would be Cp1 x1 of t plus Cp2 x2 of t plus Cdp1 u1 of t plus dp2 u2 of t plus dpm of t. So again, putting all these equations in a matrix form, it would be y of t is equal to matrix C into x of t plus d into u of t. So this is called output equation, where again x of t is equal to x1 x2 till xn is n by 1, and u of t would be u1 u2 till um, that is m by 1, and matrix C would be C11, C12, C1n, C21, C22, C2n would be CP1, CP2, CPn. P by n matrix. And D would be D11, 1, D1m, D22, sorry, 21, D22, D2m, it would be D, P1, P2, D, Pm. Which is P by M matrix. Okay. So these two equations, equation number 1 and equation number 2, right? X dot of t is equal to a into x of t plus b into x of t is together called state model of the linear time invariant system. Okay, here I should write x of t also. So x of t is equal to again x1 of t, x2 of t till xn of t. Similarly, for the output equation, it is y of t would be y1, y2 till yp. These are all vectors. Now, I'll write the equation 1 and 2 here. Equation number 1 is x dot of t into a into x of t. You must remember these two equations. The whole unit dependent on these two equations. B into u of t, first equation, and output equation y of t is equal to c into x of t plus d into u of t. Right? So these two equations are state model. State model of system. Right? Now let us draw the block diagram for these state equations. These are called state equations. Right? So we know the fundamentals of the block diagrams. We should apply those fundamentals to draw the state model or block diagram of these two equations. Right? So now what is output here? Output is y of t. So there must be, I'm writing y of t here. Now what is the input? Input must be u of t. Right. So I should draw the block diagram between input and output, right? By satisfying these two equations, right? So since it's a multivariable system, I use double lines to represent the variables. So let us start with some equation. So let us start with the first equation. So your input is multiplied with B matrix and D matrix. So input must be given to B matrix. I can represent B matrix with block B matrix. Okay, and then D matrix. So I should okay. Then so I got B into U of t and D into U of t. So this must be given to x of t, right? So I use some multiplication here. Okay, I'll use choose a summation. Right, this output. So what should be summed up? It should be A into, here I am getting B into U of t. So must be sum up with A into X of t. So this must be A, right? And this input must be X of t, right? So that I'll get here the summation of A into X of t and B into U of t. Okay. So what is that? B into U of t, A into X of t is nothing but your X dot of t, isn't it? This one only, no? I got A into X of t here, right? So I got X dot of t. So now integrate it. You will get X of t here. So I am giving this X of t, and this can be applied. So we got some, I'll just move. Now we got the U of t into the d. I'm just putting down so that d here. Now we got d into U of t, and I got X of t, and you multiply with C here, right? So the output would be summed up, that is C into X of t, right? So what is this? Y of t. Did you get it? So this is how you can write the or draw the block diagram of these state model or state equations, state model of the system. Now let us find out the state model for SISO. This is for MIMO, right? So we have multi-variables, input variables, state variables, and output variables. So the state model for SISO, that is single input, single output system. So for single input and single output system, what is the M value? M equal to 1 and P equal to 1. That is single input means you have M inputs, isn't it? Recall here you have M inputs, P outputs, and N state variables. You must remember this, right? So what should we do? For single input, single output system, we should make input M equal to 1 and P equal to 1. So what would be the state model? So it would be x of t is equal to a into x of t plus b into u of t, and y of t is equal to c into x of t plus d into u of t. So what happens? D is a constant and B and C are n by 1 and 1 by n matrices. So there is no change in the state variables. So if you want, you can see those matrices here. So D, it is P by M, P equal to 1, N equal to 1. So you have only one element. So that is constant D11 only, right? And for B and C, so C would be P equal to 1. So it is 1 by N only, right? And U will be 1 by 1. Now coming to this B value, it is N by 1. So very simple. Just substitute the values, you will get the SISO equations like this. Okay. So this is about state model of linear time invariant system for MIMO as well as SISO. Now, state space representation. So, another topic is state space representation. So generally we represent state space by two variables, physical variables and phase variables. So next topic is state space representation. By physical variables. So we have two types representation. One is physical variables, another one is phase variables. Okay. To understand this state space representation by physical variables, we just take the one physical variable system, that is RLC circuit, Assume this is your output, this is your input, and the current flowing through this. Physical. Okay. So let us stop it here. We'll continue this after tomorrow's class. So I'll summarize all the points. So we started with the basic definitions of the state, state variables, state vector, state space. Let us see all the points here. State space equations. So you have three types of variables: the dynamic system, input variables, state variables, and output variables. To know the state of the device, we use integrators as memory elements to get the status of your system. So this is your representation of your state variables. And generally, these state variables are represented by n first order differential equations. So we represented all the first order state variables. Then we have function of x of t and u of t. So since we are very much interested in LTI systems, we applied this to our LTI model, LTI system. So since it is LTI system, instead of function, it must be linear combinations of state variables and input variables. And then we wrote some matrix equations, matrices and equations. Then we found the output equation. Again, it's a function of state variables and input variables. And we represented it in the form of matrix. And equation number 1 and 2 together called state model of the system. And we have drawn the block diagram for the state model of MIMO. Then state model of SSO, just put M equal to 1, P equal to 1, we'll get the state model of SSO system. This is the introduction part, representation and state equations and state model of the LTI system. So state space representation, we have two types, biophysical variables and phase variables. So we'll consider this RLC circuit for understanding the physical variable representation of the state space. Okay.